Hey everyone, Mr. Fritz here. In this video we're going to finish our vector operations and we're going to talk about scalar multiplication of vectors. So remember what a scalar is. A scalar is just a number without any sort of direction to it. A number like 3 is a scalar number. And when we're multiplying with vectors, scalar multiplication means we're just going to take a vector that has a size and a direction and we're going to multiply it by something without a direction but with a size. So let's see what that looks like. By definition, 2 times vector A is just going to equal the sum of vector A plus vector A. And then that means that 3 times vector A should equal vector A plus vector A plus vector A. None of that stuff has changed with regular old math. And we can apply that same rule with like negative 3 times vector A. It means that you're just going to be adding 3 negative vector A's together. All that stuff should look kind of familiar with what we already know about regular old mathematics. So what we can do is let's apply this to vectors. If I have some vector A that looks like this, starting here, ending here, that is this magnitude, then I can say that 2 times vector A should be the same thing as adding vector A plus vector A. This is basically the geometric representation of what I talked about here. I can say that 3 times vector A is vector A plus vector A plus vector A, and I can say then that negative 3A is the same thing as negative vector A plus negative vector A plus negative vector A. So in general, 2A is in the same direction of A, but it's twice as long as A. So again, we have to think still about sizes and directions with these vectors. And really all that this scalar multiplication does is it either changes it only changes the length and usually not the direction unless it is oppositely directed because of a negative coefficient. So scalar multiplication is not really ever going to rotate vectors in any way. It's just going to lengthen them or change the direction of them. So let's see an example of what this looks like. We want to write out some resultant vectors based upon this. We've got a sum and some scalar multiplication given these 2 initial vectors, r that looks like this and s that looks like this. So let's start off by using the graph to graph vector r. On here, and we are going to start off with this. Let's start from here, and we want to graph vector r. Vector r is up 2 and to the right 3. So I'm going to go up 2, 1, 2, and to the right 1, 2, 3. That's one vector r, and a second vector r would be to do the same thing again, up 2 and to the right 1, 2, 3. This right here that I just graphed is vector 2r, or 2 times vector r, and I want to add s to this vector. So let's do that. S is down 2 and to the right 2. So this is be down 1, 2, and to the right 1, 2. This is vector S. The resultant vector between these two is 2r plus s, and that looks like this. And let's label that 2 times vector r plus vector s. So that's that example. And then similarly, we're going to do the same thing here where we have a vector difference or a subtraction with vectors and another scalar multiplication. So what I'm going to do, just like I did in the last video, is to visualize this vector, this negative vector s. I'm just going to sketch it over here. I'm going to start here and end here. So go in the same, or it's going to be the same size, just in the opposite direction. So let's start off with vector r again. This time I'm going to start down here and I'm going to go up 2 and to the right 1, 2, 3. There's my vector r, and let's label that vector r. Here's r, and then I'm going to subtract 3s, which is the same thing as adding negative x or negative s 3 times. So let's do that. So negative s is going to be to the left 2 and up 2. That's 1. To the left 2 and up 2, that's 2. To the left 2 and up 2, that's 3. So that right there is 3s, 3 times vector s. The resultant between these two should be whatever I get when I connect the first starting point to the final end point, and that is this resultant vector right here. And let's just label that one as well, just for good measure. Let's call that r minus 3s, vector s. So there it is. We've subtracted these vectors. We have multiplied by scalars. We've added them. Let's see if you can't put it all together. Using these 2 vectors, Show what negative r looks like, 1/2 r, 2r minus s, and then this one's kind of tricky, 1/2 times the vector r plus 3s. So give these a shot, and then when you're ready, check out the answers when you resume play. All right, here are all the answers to this final you try for these notes. Check out these solutions, see if they make sense to you, and really, right now, adding, subtracting, multiplying does not look all that different than just what normal math looks like. It's just more of a graphical representation. So things will get a little more complicated, so don't get too comfortable, and hopefully this made some sense.